Hello everyone. Today I'm going to be proving the statement if the probability of A given B is greater than the probability of A given not B, then the probability of B given A is greater than the probability of B given not A. So I'm going to start off with some key symbols. P is going to equal the probability of. This first symbol is going to equal not. The dot is going to equal times. The vertical line is going to equal given. The greater than symbol is going to be greater than, and the right facing arrow is going to represent an if-then statement. So, if the P of A given B is greater than the probability of A given not B, then the probability of B given A is greater than the probability of B given not A. So, how do you prove this? So the two things that I will be comparing are the probability of B given A and the probability of B given not A. So the probability of B given not A, or B given A, according to Bayes' theorem, is the probability of A given B times the prior probability of B times the prior probability of A. And the probability of B given not A is P, or the probability of not A given B, times the prior probability of B divided by the prior probability of not A. This is going to be equal to 1 minus the probability of A given B times the probability of B divided by 1 minus the probability of A. This is because the probability of not A plus the probability of A are going to equal 1. And so you can subtract PA from 1 and you'll get the P not A. You can subtract P not A from 1 and you'll get PA, right? So in order to compare these terms, I need to know what PA and P not A equal. So using the law of total probability, I know that the probability of A is going to be equal to the probability of A given B times the probability of B plus the probability of A given not B times the probability of not B. The probability of not A is going to equal 1 minus the probability of A. So for some definitions and setup, we're going to let the probability of B equal P, the probability of not B equal 1 minus P, the probability of A given B equals A1, and the probability of A given not B equals A0. Having these terms as placeholders is going to make it a lot more easier to do all of the math. Then I'll show how it's relevant at the end of the proof. So for the sake of this proof, we're going to assume that A1 is greater than A0. This is our hypothesis since we changed the probability of A given B to A1 and the probability of A given not B to A0. So this is just the if statement, right? If the probability of A given B is greater than the probability of A given not B, right? So this is what we're assuming, and we're trying to derive the second part of the statement from this. So from the law of total probability, we know that the probability of A is going to equal A1 times P plus A0 times 1 minus P. And the probability of not A is going to equal 1 minus PA. And PA is going to be equal to A1 times P plus A0 times 1 minus P. So it'll equal 1 minus A1 times P plus A0 times 1 minus P. Okay, I have 3 lines of converting that statement into another statement that's going to be needed for the rest of my proof, but if you're not interested in that, you can skip to the timestamp in the description. But if you want to hear how I got to the final part, I will take it step by step. So the first thing I did was I multiplied the A1 times the P, got A1P, and then I distributed the A0 to the 1 and the negative P that was inside of the parentheses, and I got 1 minus parentheses A1P plus A0 minus A0P. Alright, so the next thing I did was I then switched the order of the A0 and the A1P. It'll make it easier for me to group in the next part. So that's the next thing that I did. After that, I then distributed the negative to everything that was inside of the parentheses. So at the bottom of, or at the next line, I get 1 minus A0 minus A1P plus A0P. Next thing I do is I then switch the order of the A1p and the A0p, right? And I'm allowed to do this because it's going to equal the exact same thing, whatever order it is in. So the next line is going to be, or the next equal sign is going to be 1 minus A0 plus A0p minus A1p. Now that I have it in this form, I can then group the A0p and the negative A1p, and then I can factor out the p. So the next line is going to be 1 minus A0 plus parentheses A0 minus A1 times p. All right? The next part is going to be a little bit complicated. I'm going to multiply the 1 minus A0 times 1, which is going to keep it the same. Next thing I'm going to do is I'm going to change the 1 to a 1 minus p parentheses plus p. Because the negative p and the positive p cancel out to 0, this is going to functionally be the same thing as just multiplying it by 1, but doing this allows me to get it into the form that I'm going to need it for later. And so once I do that, I then I multiply the 1 minus A0 times the 1 minus p, and then I multiply the 1 minus A0 times the positive p, right? So I distribute it to both of these terms, and then I keep the A0 minus A1 parentheses p, keep that the same, right? So now that I've done that, I'm going to group the 1 minus A0 and the A0 minus A1, and then I'm going to factor out the p that's in both of them, okay? And then after I do that, I'm going to expand what's inside of the brackets. So we have 1 minus A0 plus parentheses A0 minus A1. Right? We expand all that, right? And we get, inside of the bracket, it's going to be 1 minus A0 plus A0 minus A1, right? And so at the next line, we have 1 minus A0 times 1 minus p plus 1 minus A0 times p. And this is the form that I needed to use Bayes' theorem. So for Bayes' theorem, I know that the probability of b given a is going to be equal to a1 times p divided by a1 times p plus a0 times 1 minus p. And the probability of b given not a is going to be equal to 1 minus a1 times p divided by 1 minus a1 times p plus 1 minus a0 times 1 minus p. We are trying to show that the probability of b given a is greater than the probability of b given not a. So we want to show that a1 times p divided by a1 times p plus a0 times 1 minus p is greater than 1 minus a1 times p divided by 1 minus a1 times p plus 1 minus a0 times 1 minus p. Given that a1 is greater than a0, a1 is the probability of a given b, and a0 is the probability of a given not b. So assuming our if statement, we want to prove the then statement, right? So let's go ahead and define f of p as the probability of b given a minus the probability of b given not a. And so we will show that f of p is greater than 0 for all p's that fall between 0 and 1 under the assumption that a1 is greater than a0, right? So if f of p is greater than 0, it means that the probability of b given a is greater than the probability of b given not a. If this is true, then it proves our statement, right? So as long as f of p is greater than 0, as long as it's a positive number between 0 and 1, between 0 and 1, it proves our statement, right? For p's that are between 0 and 1, so the second assumption is that p, which is the probability of b, this also has to be between 0 and 1. It cannot be 0 and it cannot be 1. So we have to assume that whatever this is at least conceptually possible, metaphysically possible, logically possible. If it is those, and it's not obviously 100% proven, then this proof is also going to work. Okay, so f of p is going to equal a1 times p divided by a1 times p plus a0 times 1 minus p divided by 1 minus a1 times p divided by 1 minus a1 times p plus 1 minus a0 times 1 minus p. So to compare these fractions, we have to use a method called the difference of fractions. So we're going to multiply the left side of this equation by, or the top and the bottom of the left side, by what's on the bottom of the right side. So what we're going to do is we're going to multiply a1p and a1 times p plus a0 times 1 minus p by the denominator of the right-hand equation. So 1 minus a1 times p plus 1 minus a0 times 1 minus p. And then we're going to multiply the top and bottom of the right side by the denominator of the first equation, which is a1p plus a0 times 1 minus p. So you multiply it by the top and the bottom, and this allows us to combine them into one fraction with the minus sign just in the middle. All right, and so our next equation is going to be, once we've combined everything, a1p times 1 minus ap plus 1 minus a0 times 1 minus p minus 1 minus a1 times p times a1p plus a0 times 1 minus p divided by a1p plus a0 times 1 minus p times 1 minus a times p plus 1 minus a0 times 1 minus p. So let's denote the numerator as n of p. We only need to show that the numerator is greater than 0 because the denominator is clearly positive for 0 less than p less than 1. How do we know this? So the denominator has a1, it has p, it has a0, and it has the number 1. We've already established that in our if statement that a1 and a0 are positive non-zero numbers. And we are assuming, for the sake of this, that we have not proved them to be true, and they are at least logically possible, so that they're not 0 and they're not 1. And we know that a1 is greater than a0. And we also know that p has to be a non-zero number, right? If p is 0, then this proof does not work. So once this relies on the assumption that the probability of b, the prior of b, is going to be greater than 0. So it has to be at least possible, right? So if we assume that, then the denominator is going to be clearly positive. There's no way for it to be negative at all, and it can't be 0 either. So we don't have to look at the denominator, we only have to look at the numerator, right? So let's expand n of p. N of p is going to equal a1p times 1 minus ap plus 1 minus a0 times 1 minus p minus 1 minus a times p times a1p plus a0 times 1 minus p. We're then going to factor out the p from both sides of the minus sign. So we have p bracket times a1 times 1 minus ap plus 1 minus a0 times 1 minus p minus 1 minus a1 times a1p plus a0 times 1 minus p. Next, we're going to expand the brackets. So inside the bracket, we're going to go ahead and distribute the a1 to the 1 minus a times p and to the 1 minus a0 times the 1 minus p. So we have a1 times 1 minus a1p plus a1 times 1 minus a0 times 1 minus p. Then we're going to distribute the 1 minus a1 and the negative. We're going to distribute both of those to the a1p and the a0 times 1 minus p. That's going to get us a negative a1 times 1 minus a p minus an a0 times 1 minus a1 times 1 minus p. Next, we're going to cancel matching terms. So a1 times 1 minus a1p cancels with negative a1 times 1 minus a1p. And that is going to be the first and the third term inside of the bracket, so we can cancel those out. Leaves us with the second and the fourth term, which is a1 times 1 minus a0 times 1 minus p minus a0 times 1 minus a times 1 minus p. Next thing that we can do is we can factor out the 1 minus p. So we get n of p equals p times 1 minus p times bracket a1 times 1 minus a0 minus a0 times 1 minus a1. Next thing we can do is we can distribute within the bracket, and we get, within the bracket, we're going to get a1 minus a1 times a0 minus a0 plus a1 times a0. we can go ahead and combine like terms. The negative a1, a0, and the positive a1, a0 are going to cancel out and equal 0. That means n of p equals p times 1 minus p times a1 minus a0. So we have f of p equals p times 1 minus p times a1 minus a0 over a positive denominator. Now, under the assumption that a1 is greater than a0, i.e. the probability of a given b is greater than the probability of a given not b, which is our if statement. So if we assume this is true, and we assume that p is between 0 and 1, so the prior probability of b is between 0 and 1, then it would follow that p times 1 minus p times a1 minus a0 has to be greater than 0. And so that would mean that f of p is greater than 0. So therefore, the probability of b given a is greater than the probability of b given not a, since f of p is equal to p, the probability of b given a, minus the probability of b given not a, and since that number is greater than 0, it means that the probability of b given a is higher than the probability of b given not a. So the conclusion would be that if the probability of a given b is greater than the probability of a given not b, then the probability of b given a is greater than the probability of b given not a. Thanks for watching, and I hope you enjoyed this video.